There is this mathematical proof in standard logic that guarantees the statement, tomorrow there will be a sea battle, is 100% true or 100% false right this very second.
Right, which sounds, totally fine at first glance.
Yeah, it sounds like basic common sense. But thousands of years ago, philosophers realized that if they just blindly accepted that simple mathematical rule, they might accidentally destroy the entire concept of human free will.
Exactly, because if the truth of tomorrow's battle is literally already fixed today, then the Admiral's choices, they mean absolutely nothing.
Right. So today, for this deep dive, we are opening the hood on human thought. We are looking at the underlying machinery of how we argue, how we prove things, and how we actually define truth itself.
It really is, it's about transitioning from just experiencing a debate to understanding the hidden architecture behind it all. I mean, we all know how to argue, right? We use logic every day. But understanding the actual mechanics of that logic is an entirely different skill set.
I always kind of think of it like a symphony. Usually we just sit back and let the sound wash over us. You tap your foot, you hum the melody, you're just experiencing the music.
Yeah, you're in it.
Exactly. But then someone hands you the sheet music, and suddenly you're not just hearing a tune, you are looking at time signatures and chord progressions and mathematical intervals.
Right, you finally understand the structural reasons why those specific notes sound so powerful together.
Yes. And that transition from listener to reader is sort of the perfect framework for what we are doing today. Our source material is Theodore Sider's Logic for Philosophy, and the stated mission of this text is to give you, the listener, something he calls logic literacy.
Logic literacy, I really love that term.
Me too. And I love the quote Sider uses in the preface. He says this material is meant to prepare you to read highly sophisticated philosophy, and specifically, and this is great, to help you resist bullying by symbol mongers.
Oh, we have all encountered those symbol mongers.
Oh, absolutely. You're reading a dense article or you're in a meeting and someone just wants to shut down the debate. So they start throwing around formal logical symbols or heavy mathematical sounding jargon.
Right. It's meant to be intimidating. It creates this artificial barrier to entry to make you feel like you can't participate.
Exactly. So today's deep dive is about giving you the toolkit to see right through that tactic. But, to acquire that toolkit, we have to recognize a massive distinction right out of the gate. We are not just sitting down to learn how to do basic logic today.
Far from it. We are stepping up an entire level of abstraction to learn meta logic.
Okay, let's unpack this. If I take a Logic 101 class in college, I'm learning how to translate English sentences into symbols, and I'm drawing those little truth tables to see if an argument works. That's doing logic.
Right.
So how exactly does meta logic change the game?
Well, think of it this way. The Logic 101 student is learning how to use a hammer and a saw to build a house, right? They're inside the system, they're using the tools. Meta logic is what happens when logicians step out of the house, lay the tools on a workbench, and start studying the tools themselves as mathematical objects.
Oh, interesting.
Yeah, they ask questions about the hammer, like, what is it made of? Are there mathematical limits to what it can build? Will this saw inevitably break if I use it on a specific type of wood?
So if doing logic is playing a game of chess, metalogic is stepping back and asking, is it mathematically possible for a game of chess to go on forever? Is there structural flaw in the rules themselves?
That captures it perfectly. I mean, in a world characterized by massive information overload, understanding metalogic is like the ultimate shortcut to clear thinking.
Because you're looking at the system itself.
Exactly. When you understand how the systems of truth preservation operate from the outside, you can evaluate the structural integrity of literally any argument, entirely independent of how emotional or complex the actual topic is.
So to build that superpower, we need to start at bedrock. Because before we can study these logical systems from the outside, we have to figure out what genuine logic actually is, right? What is the core phenomenon we are even trying to study?
Right. And the text grounds this in a concept called logical consequence.
Logical consequence.
Yeah, it's the beating heart of the whole field. And the defining slogan for it is, and this is important, truth preservation by virtue of form.
Truth preservation by virtue of form. Okay, that is dense. Let's ground that with the textbook's example of the apple. If I hold an apple out in front of me and just let go, we all know what happens.
It falls to the floor.
Right, so if I give you the premise the apple was dropped, does it logically imply the conclusion the apple fell?
Well, according to the strict rules of genuine logic, no. And that shocks a lot of people.
Because it feels undeniably true. I mean, it's gravity,
Right. It is physically true.
Mm.
The relationship between dropping the apple and the apple falling is a causal relationship. It's governed by gravity,
Yeah.
but it is not a logical relationship.
Oh, I see.
The truth is preserved by the laws of physics, not by the sheer structure of the sentence itself.
Right, because I can easily imagine like a sci-fi universe where gravity works differently. And when I drop the apple, it just hovers there or, I don't know, shoots up to the ceiling. The words dropped and fell don't have this mathematically necessary connection binding them together across all possible realities.
Exactly. Now contrast that physical necessity with a genuine logical consequence. Consider the premise. Grant is male.
Oh,
Does that premise logically imply the conclusion, someone is male?
oh, yes. I mean, there is absolutely no universe, no alternate dimension where it is true that Grant is male, but somehow false that someone is male. It's an airtight guarantee.
And notice where that guarantee comes from. It doesn't rely on physics or biology or even, who Grant actually is. It is truth-preserving purely by virtue of its form.
It's structure.
Yes, the structure makes it impossible for the premise to be true while the conclusion is false.
It's like a perfectly sealed pipe, you know? If you pour truth into the top, the shape of the pipe guarantees that truth will come out of the bottom, the conclusion.
That's a great way to look at it.
And the pipe doesn't care if you're pouring water or oil or sand. The content totally doesn't matter. The form is doing all the work.
Which naturally leads us to the concept of a logical truth. If a logical consequence is an argument that preserves truth through its pipe-like structure, a logical truth is a sentence that generates truth all on its own, with literally no premises required.
So if a logical truth requires no premises, does that mean it's just something totally self-evident, like saying a triangle has 3 sides?
Well, that's the trap most people fall into.
Yeah.
But logicians draw a hard line there.
Really? Why?
Because the truth of a triangle having 3 sides relies on the dictionary definition of the word triangle. It relies on content.
Oh, right.
A genuine logical truth must rely only on structure. So a better example would be, if it is a triangle, then it is a triangle, or all fish are fish.
Okay, wait, let me try to break that. Because you said form is the absolute only thing that preserves truth and logic.
Right.
What if I give you this premise? Grant is a bachelor. The conclusion is Grant is unmarried. I know for an absolute fact he is unmarried if he is a bachelor. The truth perfectly transfers over. Why isn't that considered a logical consequence?
You are hitting on a major boundary line in philosophy right there.
Yeah.
You are entirely correct that it is impossible for Grant to be a bachelor and not be unmarried. But logicians reject that as a logical consequence because the truth is being preserved by the internal definitions of the words bachelor and unmarried.
Oh, okay.
It is a semantic guarantee, not a structural one.
So where do they draw the line? Like, what counts as structure?
Logicians identify a very specific set of words called logical constants. These are like the structural load-bearing walls of any language. Words like and, or, not if, then, all, and some. They treat these words as the rigid framework. Every other word, bachelor, unmarried, grant, apple, that's just non-logical vocabulary. It's the drywall, the paint, the furniture. In logic, we completely ignore the drywall.
Oh, wow, I see. So when a logician looks at the sentence, if Grant is a bachelor, then Grant is unmarried, they delete the drywall. They delete Grant, bachelor, and unmarried. They just see placeholders. They see if X, then Y.
Exactly. And is the form if X, then Y guaranteed to always be true?
Definitely not. I mean, if my car is blue, then it is raining. That's an if X, then Y form, and it's obviously not guaranteed. So the structure alone failed to preserve the truth.
But now look at an argument that relies only on logical constants. Let's say Liesel is a swimmer, and Liesel is famous. Therefore, Liesel is a swimmer.
Okay.
The only logical constant there is and. The skeleton is X and Y, therefore X.
And that skeleton is indestructible. No matter what nouns or verbs you plug into X and Y, if the premise is true, the conclusion is absolutely guaranteed to be true. That is genuine logical consequence.
Which brings us to a significant hurdle. If logic depends strictly on these structural constants and, not or, we have to reckon with the fact that human language is a terrible place to study them.
Yeah, English is messy.
It's incredibly messy. It is full of ambiguity, slang, idioms, and shifting meanings.
Yeah, like if I say, you can have soup or salad, the or usually means you get one, not both.
Right.
But if a sign says discount for students or seniors, and you are a student and a senior, you still get the discount. The word or behaves completely differently depending on the context.
Which is a complete disaster if you are trying to build a rigorous mathematical science of truth preservation. You cannot have load-bearing walls that shift their shape depending on the weather.
No, that wouldn't work at all.
So logicians abandon natural language. They build formal artificial languages. This is where we move into the sandbox.
And when we build this pristine mathematical sandbox, the text emphasizes a critical divide that we absolutely have to maintain. It is the distinction between the object language and the meta language.
Okay.
And, this seems like something that could easily trip up a beginner.
Oh, it trips up professionals if they aren't careful.
Yeah.
The object language is the formal symbolic language that we are actively studying. It is the object of our investigation. It consists of the artificial symbols, the P's and Q's, the little wedge symbol for and, the arrow for if.
And the meta language.
The meta language is the language we use to talk about the object language.
Huh.
For you and me, right now, our meta language is English.
So if I write a massive algebraic logic formula on a whiteboard, that formula is the object language.
Yes.
But if I turn to you and say, hey, that formula on the board has 5 variables, my English sentence is the meta language. I am making a claim about the formal system.
You are. And maintaining the strict boundary between the thing you are studying and the language you use to describe it leads to one of the most pedantic yet utterly crucial distinctions in all of philosophy. It's called the use versus mention distinction.
Sider gives an incredibly memorable example for this. Listen to the sentence. Philadelphia is made up of 12 letters.
If you say that, you are technically uttering a falsehood.
Which sounds completely insane at first, but it makes perfect sense when you pause and think about it. Philadelphia, the actual physical city, is not made up of letters.
No, it's made up of buildings.
Right. It's made up of asphalt, skyscrapers, streetlights, and millions of people. The city doesn't have 12 letters. The word that names the city has 12 letters.
Exactly. To state a true fact, you have to say, quote, Philadelphia, unquote, is made up of 12 letters.
Yeah.
In the first false sentence, you're using the word to point out into the real world at the city. In the second true sentence, you are mentioning the word. You are referring to the linguistic artifact itself. You put it in quotation marks to signal, I am talking about the symbol, not the thing the symbol represents.
Why are logicians so obsessed with this level of grammatical pedantry? Like, does it really matter that much in practice?
In metalogic, it is the difference between the sandbox holding together and completely collapsing.
Wow.
Yeah. We are constantly manipulating symbols that represent truth, falsehood, and reality. If you accidentally confuse a symbol for the reality it represents, your entire mathematical proof will derail. You have to be ruthlessly precise about whether you are using a symbol to claim a truth about the world or mentioning a symbol to analyze its structural properties.
Okay, so we have our perfectly sealed sandbox, we have our artificial object language, and we are using our English meta language to carefully talk about it without mixing up use and mention. What exactly are we trying to model in here? Like, we know we want to capture genuine logical consequence, but how do we mathematically define that?
That is where the text reveals something truly fascinating. There isn't just one mathematical way to define it. The nature of logical consequence is actually a fierce philosophical debate.
Oh, really?
Yeah. Sider outlines 4 major frameworks for defining what makes a consequence genuine: semantic, proof theoretic, Quinian, and modal.
Okay, let's explore these because it really shows how logic isn't just a monolithic block of math, it's a series of philosophical choices. The dominant one today is the semantic approach, right? The text also calls this the modal theoretic answer.
Yes. The semantic approach says that a logical consequence is valid if, whenever you hold the meanings of the logical constants absolutely fixed, but you vary everything else about the world. You change the non-logical words, you change the state of reality, the argument always survives.
So it's like you keep the structural frame of the house identical, the ands and nots stay put. But you swap out the drywall, you change the furniture, you even pick the house up and drop it in a completely different universe. If the house never, ever collapses, then the conclusion is a genuine semantic consequence of the premises.
Beautifully put. You are evaluating truth across all possible models or interpretations. Now, contrast that with the proof theoretic answer.
This one sounds much more mechanical.
It is entirely mechanical.
Yeah.
The proof theoretic approach doesn't care about evaluating truth across parallel universes or models. It says consequence is purely about provability.
Okay.
It is about whether you can transition, step by step, from the premises to the conclusion using a strictly defined set of acceptable rules of inference.
So if the semantic approach is a bird's-eye view, mapping the territory of all possible truths, the proof-theoretic approach is on the ground asking, do I have a legal set of stepping stones to walk from premise A to conclusion B?
That's a great distinction. Then we have the Quinian answer, named after the philosopher W.V.O. Quine. This approach focuses heavily on grammar and substitution. Quine argued that a conclusion follows logically from premises if and only if there's no way to uniformly substitute the non-logical vocabulary to make the premises true and the conclusion false.
Let's do a mental exercise with this one so you listening can really feel how Quine's test works. Let's take a classic valid argument. All dogs are mammals. Fido is a dog, therefore Fido is a mammal. To apply Quine's test, we have to try to break it, right? We have to swap out the nouns to create a version where the premises are true, but the conclusion is a lie.
Right, but we keep the constants. All R is A, therefore.
Okay, so let's try to substitute. All birds are animals. A robin is a bird, therefore a robin is an animal. Premises are true, conclusion is true, the argument held. Let's try harder to break it. All cars are planets. Wait, no, that premise is false. Quine's test requires us to start with true premises. Let's try. All surgeons are doctors. Sarah is a surgeon, therefore Sarah is a doctor. Still true. The reality is you can play this game for the rest of your life and you will never find a combination of nouns that breaks that specific skeleton. Because it cannot be broken by uniform substitution, Quine declares it a genuine logical consequence.
Perfect. And finally, we have the modal answer, which is arguably the most intuitive for people outside of mathematics. It relies on the concepts of necessity and possibility. It simply states that a conclusion follows from premises if it is absolutely metaphysically impossible for the premises to be true, while the conclusion is false.
So if Quine is just aggressively swapping out nouns and the modal approach is dreaming up parallel universes of impossibility, they are fundamentally prioritizing different things. One is heavily focused on language and syntax. The other is focused on metaphysics. Why does Sider spend so much time outlining all four of these? Why doesn't he just tell us which one is right?
Because Sider wants you to remember that logic is a branch of philosophy. Most modern textbooks just stipulate the semantic and proof-theoretic models as absolute, unquestionable dogma. They teach the math and ignore the meaning.
Makes sense.
But Sider is showing us that these formal systems are just human-made models attempting to capture the incredibly elusive nature of truth. When logicians build a system, they're making profound philosophical assumptions.
And when philosophers disagree on those assumptions, they don't just write angry essays, they actually build different mathematical sandboxes. This leads us perfectly into Section 4, Tinkering with the Rules. Sider outlines 3 ways that logicians alter standard logic when it doesn't fit their philosophical worldview: extensions, deviations, and variations.
Let's look at extensions first. Standard logic is powerful, but its vocabulary is limited. It can't handle concepts like time or moral obligation or necessity. It can't translate a sentence like, it is necessarily true that 2 plus 2 is 4.
Right.
So logicians create an extension. They add new symbols and rules to standard logic to give it more expressive power without deleting anything old.
For instance, they might add a little box symbol to represent necessarily, creating modal logic. It's like buying an expansion pack for a board game. You still have the original board, you just have more cards to play with.
Deviations, however, are much more radical. A deviation is when a logician looks at the standard rules of classical logic and says, these rules are fundamentally wrong. They keep the same symbols, but they alter the core mathematical laws governing them.
You mentioned the sea battle hook at the very beginning of the deep dive. This is the ultimate example of a deviation, and it blew my mind when I first read it. Walk us through how classical logic handles the sea battle.
Okay, so in classical standard logic, there's a foundational pillar called the law of excluded middle. It dictates that every single statement must be entirely true or entirely false. There's no middle ground.
Okay.
Consequently, any statement structured as P or not P is a tautology. It is always true.
Like, it is raining or it is not raining. That is 100% true, always.
Exactly. But then Aristotle posed this problem. Consider the sentence. Either there will be a sea battle tomorrow or there will not be a sea battle tomorrow. Standard logic demands that because it is a P or not P structure, that sentence is an absolute truth right now, today.
But if it is mathematically true today that a specific event will or will not happen tomorrow, doesn't that imply the future is locked in? If the truth value is already fixed, the admiral has no real choice. Free will becomes an illusion created by our ignorance of the math.
And many philosophers find that metaphysical implication unacceptable. They believe the future is open. So they create a deviant logic. Specifically, they build a three-valued logic. Instead of just true and false, they introduce a third truth value, indeterminate.
Oh, wow. How does that mechanically solve the sea battle problem?
In this deviant sandbox, the statement, there will be a sea battle tomorrow, let's call that P, is assigned the value indeterminate because the event hasn't happened yet.
Makes sense.
The negation, there will not be a sea battle tomorrow, not P, is also indeterminate. So when you evaluate the full sentence, P or not P, which is indeterminate or R, indeterminate, the mathematical output is indeterminate, not true.
Wow, they literally break the law of excluded middle. P or not P is no longer a guaranteed tautology. They alter the mathematical engine of logic specifically to rescue human free will from determinism.
It perfectly illustrates that logic is not just cold algebra. The rules you choose deeply reflect how you view time, reality, and human agency.
That is incredible. And just to round out the list, the third way to tinker is variations.
Variations are minor. You just change the notation without changing the rules or the philosophy.
Right.
Like Polish notation. Instead of writing the operator in the middle, like P or Q, you write it at the front. Or PQ. It is exactly the same logic, just written with a different syntax.
So we've seen how philosophers debate consequence and how they tinker with the rules of the sandbox to fit their worldview. But if you want to actually build these deviant sandboxes and rigorously prove that they work, you can't just use English. You need a mathematical engine. And the engine logicians settled on is set theory.
Set theory is the heavy machinery of meta-logic.
Yeah.
You cannot prove things about logical systems without it. And you cannot understand set theory without grappling with its most fascinating and, frankly, unsettling aspect, the nature of infinity.
Okay, let's start with the basics before we break our brains. What is a set?
A set is simply a collection of things, which we call its members. You can have a set of the even numbers between 1 and 10. The members are 2, 4, 6, and 8. You can have a set of the planets in our solar system. A set can contain anything.
And we use a little curved E symbol to denote membership. Like 2 is a member of the set of even numbers. And crucially, we can have sets with an infinite number of members, like the set of all natural numbers. 0, 1, 2, 3, going on forever.
But right at the foundation of this seemingly innocent concept, early logicians ran into a catastrophic problem. If a set can contain anything, can a set contain other sets? Yes. Can a set contain itself? This single question led Bertrand Russell to discover a paradox that nearly destroyed mathematics.
Oh man, let's trace the logic loop of Russell's paradox. Because this is wild. Russell says, imagine a very specific set, let's call it set R. Set R is defined as the set of all sets that do not contain themselves as members. It is the collector of all non-self members.
This makes intuitive sense, right? Most sets don't contain themselves. The set of all planets is not a planet, so it doesn't contain itself. Therefore, the set of all planets would be allowed inside set R.
So set R is gathering up all these normal, non-self-containing sets, but then Russell springs the trap. Is set R a member of itself?
Try to answer, there are only two options.
Okay, let's play it out. Option 1, set R is not a member of itself. But wait, set R was explicitly defined as the set of all non-self members. So if it is a non-self member, it qualifies to be in set R, which means it is a member of itself, a contradiction.
Right, so try option 2.
Option 2, set R is a member of itself. But set R only allows sets that are non-self members inside. So if it's inside, it must be a non-self member, which means it isn't a member of itself. Another contradiction.
It is a vicious, inescapable circle. Every time you declare a state, it immediately implies its own opposite. This paradox proved that the intuitive, freewheeling idea of sets, where you can just define a collection however you want, was mathematically broken.
So modern set theory introduces incredibly complex axioms specifically designed to restrict how sets are formed, to avoid these paradoxical loops. We won't get bogged down in those axioms today. We'll just stick to safe sets, like sets of numbers.
Exactly. With safe sets, we can start comparing them using functions. A function takes an input from a domain set and maps it to an output in a range set.
And the most important function for our purposes is the one-to-one function. That is a function where every single input maps to a completely unique output. No two inputs ever point to the same output.
One-to-one functions are the key to unlocking the weirdness of infinity, because set theorists use them to measure the size of sets. They call it equinumerosity.
Equinumerosity, sameness of size.
Two sets are equinumerous. They're the exact same size if you can create a perfect one-to-one function between them, meaning you can perfectly pair up every member of set A with a unique member of set B with nothing left over on either side. If you have a set of 5 chairs and a set of 5 people, you can pair them up perfectly. The sets are equinumerous.
That makes perfect sense for finite objects. But when you apply that exact same logic to infinite sets, the results are deeply unsettling. Let's compare the infinite set of all natural numbers 0, 1, 2, 3, going on, with the infinite set of even numbers 0, 2, 4, 6, 8. Which set is bigger?
Common sense dictates the natural numbers must be bigger. It contains all the even numbers plus an infinite amount of odd numbers. It feels like it should be twice as big.
But mathematically, they are the exact same size. They are equinumerous.
Because we can line them up perfectly with a one-to-one function. We map 0 to 0, we map 1 to 2, we map 2 to 4, we map 3 to 6. For every single natural number, let's call it, and we map it to 2.
Right. Every natural number gets a unique even number, and every even number will eventually be hit by a natural number. There are no numbers left over. So a set can be exactly the same size as a subset of itself. That is wild. Let's push it harder. What about rational numbers, fractions?
This is where it gets truly counterintuitive. Fractions are dense. Between any two whole numbers, like 1 and 2, there are infinitely many fractions. Between 12 and 34, there are infinitely many fractions. Surely this dense sea of fractions represents a fundamentally larger infinity than the simple counting numbers.
But it doesn't. The set of all fractions is also the exact same size as the natural numbers. And the proof for this involves visualizing an infinite grid. Imagine a two-dimensional grid stretching out forever. The columns across the top are the numerators, 0, 1, 2, 3. The rows down the side are the denominators, 1, 2, 3, 4.
Every possible fraction exists somewhere at an intersection on this grid. 12 is in the second column, second row. 1003 is way out in the 101st column, third row. The entire infinite universe of fractions is on this 2D plane.
So how do we map a 2D plane to a 1D list of counting numbers? We draw a spiraling path. We start at the top left at 0, 1, and we map it to 0. Then we move in a counterclockwise expanding square. We step down to 0, 2, map it to 1, move right to 12, map it to 2, up to 11, map it to 3.
We keep tracing these expanding concentric rectangular rings. We are drawing a single continuous one-dimensional line that will eventually spiral through every single intersection on this infinite grid.
Now, some fractions have the same value. 12 is the same as 24. We don't want to count them twice because our function must be 1 to 1. So as we trace our spiral, if we hit a value we've already counted, we just skip it and move to the next intersection.
Because this spiraling path will eventually reach every single coordinate on the grid, every single unique fraction will eventually be assigned a unique counting number, 0, 1, 2, 3, 4. The list goes on forever, but it is a single list. The dense, infinite sea of fractions is exactly the same size as the counting numbers. They are both what we call countably infinite.
Okay, so is that it? Is infinity just infinity? Are all infinite sets the same size?
No. Here is where the floor drops out. There are different sizes of infinity. Some infinities are mathematically uncountably larger than others, and the proof for this is Georg Cantor's diagonal argument. It is an absolute masterpiece of logic.
We are going to look at real numbers, decimals. These include fractions, but they also include irrational numbers whose decimals go on forever without repeating, like pi or the square root of 2. We are going to prove that the set of real numbers is a larger infinity than the natural numbers.
And we prove it by contradiction. We assume they are the same size. If they were the same size, we could create a perfect one-to-one function. We could create a complete infinite list of every single decimal number between 0 and 1, perfectly paired with the natural numbers 0, 1, 2, 3.
We assume this hypothetical list is 100% complete. Every possible decimal is on it.
Now, Cantor says, I can construct a real number that is mathematically guaranteed not to be on your complete list. Let's call this new number D.
How does he build D? He builds it digit by looking at the diagonal of the list. We look at the very first number on our list, and we look at its first digit after the decimal. If that digit is a 5, we make the first digit of our new number E's a 6. If it's anything else, we make it a 5.
We move to the second number on the list. We look at its second digit. If it's a 5, the second digit of D becomes a 6. If not, it becomes a 5.
We move diagonally down. For the 500th number on the list, we look at the 500th digit, and we make sure the 500th digit of D is different. We do this infinitely. We have now generated a completely new infinite decimal D.
And here is the lethal question. Could this new number be hiding somewhere on your original list?
It is structurally impossible. It can't be the first number on the list because we forced the first digit to be different. It can't be the second number because the second digit is different. It can't be the billionth number because the billionth digit is different. D differs from every single number on the list in at least one decimal place.
Therefore, D is not on the list. But D is a real decimal number. which means our initial assumption that we could create a complete list was false. It is mathematically impossible to list all the real numbers and map them to the natural numbers. The set of real numbers is fundamentally uncountably larger. It is a bigger infinity.
Now, I have to jump in because when I first encountered this, my brain immediately tried to find a loophole. I thought, okay, deed isn't on the list. Why don't we just take deed, slap it onto the very top of the list, bump everything else down one spot, and boom, the list is complete again.
Oh, it's the most natural objection. Everyone thinks that.
Yeah.
But the text provides a brilliant analogy to explain why that doesn't work. Imagine a restaurant with a fixed maximum capacity. If a crowd of 1,000 people shows up, some people are going to be left standing outside.
Right.
You can change who gets inside. You can kick someone out of the booth and let someone from outside come in. You can add deed to the list. But the moment you do, Cantor will just run his diagonal process over your new list, and he will generate a new number, GDEX2, that is left outside.
Oh, man.
The problem isn't that deed is a magic unlistable number. The problem is that the restaurant of the natural numbers simply doesn't have enough seats to hold the population of the real numbers. No single list can ever capture them all.
That is just, it shifts your whole perspective on how massive the mathematical universe really is. But let's tie this back to our primary mission today. Why do we need to understand infinities and functions and sets? Because we have to build our sandbox. We need this mathematical engine to construct the formal language of propositional logic, or PL.
Exactly. We use set theory to rigorously define both the grammar and the semantics of PL. Let's start with grammar. How do we mathematically mandate what a legally constructed sentence looks like? We define well-formed formulas, or WFFs, and we do this using a recursive definition.
A recursive definition. The text refers to this as benign circularity. Unlike Russell's paradox, which was a vicious, destructive circle, this is a structured, productive loop.
Yes, a recursive definition has two main components, a base clause and an inductive clause. The base clause provides the solid anchor. In PL, the base clause states, every single sentence letter P, Q, R is automatically a WFF.
Then we have the inductive clause, which tells us how to build more complex structures out of the simple ones. It says, if phi and psi are already WFFs, then the negation not phi and the conditional phi implies psi are also WFFs.
And you finish with a closure clause stating that nothing else is a rough. So if I hand you a massive, complex string of symbols and ask, is this legal? You just trace it backwards through the inductive rules. If you can eventually deconstruct it down to the solid bedrock at the base clause sentence letters, it is legal. That is benign circularity.
Now notice something really fascinating about that grammar rule. We only use two logical constants, the tilde for not and the arrow for ifin. What happened to and or?
We don't actually need them as primitive symbols. This demonstrates the incredible efficiency of PL. You can mathematically define all the other connectives purely using ifin and not.
Let me break this down for you, because seeing this translation for the first time is a real light bulb moment. How do you say P and Q using only if and not? You write it as, it is not the case that if P is true, then Q is false.
And to trace the logic there. If it's not true that P implies not Q, the only possible scenario where that works is if P and Q are both true at the exact same time. Structurally, it means the exact same thing as P and Q.
That's so elegant.
By restricting our primitive language to just two symbols, we make the meta logic vastly simpler, because later on, we have far fewer rules we need to prove things about.
Okay, so that is the grammar, the syntax. Now we need semantics. How do we assign meaning or truth to these symbols?
We use a valuation function. This is a set theoretic function, just like the ones we discussed earlier. A PL interpretation is a function that assigns either a 1 representing true or a 0 representing false to every single sentence letter.
So P is mapped to 1, Q is mapped to 0, R is mapped to 1.
Correct. And then the valuation function maps human truth conditions into strict mathematical operations for the complex formulas. The rule for negation is simple. It flips the value.
Yeah.
If P is 1, not P is 0.
But the rule for the conditional, the if-then arrow, is notoriously tricky for beginners. The mathematical rule is a conditional evaluates to 1 true in every scenario except when the premise is 1 and the conclusion is 0.
This confuses a lot of people. They ask, why does a false premise mathematically make the entire conditional statement true?
Think of it like a promise. Let's say I promise you, if you mow my lawn, then I will pay you $50. Now imagine you don't mow my lawn. My premise is false, and I don't pay you. Did I break my promise?
No. Your promise remains completely intact.
Exactly. I only break the promise if you mow the lawn. Premise is true, and I refuse to pay you. Conclusion is false. If you don't mow the lawn, My if-then statement hasn't been violated, so mathematically the logic evaluates it as true by default. We have translated a human concept into a flawless mathematical function.
So we have our grammar and we have our semantic truth values. This brings us to section 7, proving it. If I hand you a complex argument in PL, how do we actually prove that the conclusion follows from the premises? If we rely solely on the semantic valuation functions, we have to draw massive truth tables. For a formula with 5 variables, you have to calculate 32 different rows of ones and zeros.
Yeah, it's agonizing and incredibly inefficient. So instead of checking every possible universe, we use proof theory. We manipulate the symbols syntactically, step by step on a piece of paper. And the text introduces 2 radically different ways to do this: sequent proofs and axiomatic proofs.
Let's look at sequent proofs first. This system uses a symbol that looks like a double arrow, and it is designed to mimic natural human reasoning, primarily because it allows you to reason using assumptions.
In everyday life, we use assumptions all the time. If I want to prove if it rains, the grass will be wet, I start by assuming it rains. I treat it as a temporary fact. I trace the causal logic to the wet grass. Once I get there, I discharge my assumption and conclude the if-then statement. Sequent proofs formalize this with rules like conditional proof and reductio ad absurdum proof by contradiction.
Feels very natural. But then we encounter axiomatic proofs, and axiomatic proofs are incredibly, famously hostile to the user.
They are brutal. In an axiomatic system, you are absolutely forbidden from making assumptions. You cannot use conditional proof.
So what are you allowed to use? You are given a small list of axioms. These are complex structural formulas that are stipulated as foundational truths, and you are given exactly one rule of inference. Modus ponens.
Only one rule.
Modus ponens says, if you have a line that says phi implies pi, and you have a line that says phi, you can infer a new line that says pi. That is your entire toolkit. Every single proof must be hammered out using only modus ponens and the axioms.
To understand how agonizing this is, imagine trying to prove a simple tautology. P implies P. In a sequent proof, you assume P on line 1, you reiterate P on line 2, you discharge the assumption, and you're done in 3 lines.
Easy.
In an axiomatic proof, you can't assume P. You have to start with a massive, unwieldy axiom like axiom 1. Phi implies that psi implies phi. You have to substitute P's and Q's into it, find another axiom to match it with, and carefully execute modus ponens over and over, generating massive strings of symbols just to shave them back down to P implies P. It takes 5 lines of dense algebra to prove something painfully obvious.
Which naturally raises the question, if axiomatic proofs are incredibly rigid, forbid natural assumptions, and take 5 lines to prove what a sequent proof does in 3, why did logicians invent them? Why create such a user-hostile sandbox?
This is where the difference between doing logic and doing metalogic really shines.
Axiomatic systems are agonizing for the logic student trying to prove a theorem. But they are a dream come true for the metalogician who is trying to prove properties about the system itself.
Why does making it harder to use make it easier to study?
Think about the math. If you want to mathematically prove that your logical system possesses a certain property, say that it never produces a contradiction, and your system is a sequence system with 15 different rules of inference, you have to write a mathematical proof for every single one of those 15 rules.
Oh, that sounds awful.
But if your system is axiomatic, you only have one rule, modus ponens. You only have to prove that your starting axioms possess the property and that modus ponens preserves the property. The metalogical proof becomes radically shorter and more elegant.
You purposefully sacrifice ease of use inside the sandbox to make it mathematically simple to inspect the sandbox from the outside.
Exactly. And, logicians aren't completely heartless. They developed a metalogical shortcut called the deduction theorem to make axiomatic proofs slightly less painful.
The deduction theorem is brilliant. It's essentially a metalogical guarantee. It proves that if you were able to prove psi by temporarily taking phi as a premise, then there absolutely exists a strict axiomatic proof of the conditional phi implies psi's. It allows logicians to simulate the ease of conditional proof in their daily work while resting on the mathematical guarantee that the strict axiomatic rules haven't been violated.
Okay, we have finally reached the summit, section 8, tying it all together. Over the course of this deep dive, we have constructed 2 completely parallel universes. We have the semantic universe, where consequence is defined by evaluation functions mapping ones and zeros to models. And we have the syntactic proof-theoretic universe, where consequence is defined by physically manipulating symbols using modus ponens.
2 entirely different conceptual models what logic even is. The ultimate question of metalogic, the holy grail, is, Do these two universes perfectly mirror each other?
And the staggering achievement of standard propositional logic is that, yes, they do. They map perfectly onto one another. And the proof of this alignment relies on two massive concepts: soundness and completeness.
I like to think of soundness and completeness like a judicial system. What is soundness?
Soundness dictates that every single theorem, every formula you can possibly prove using your syntactic rules is guaranteed to be valid, guaranteed to be semantically true in all models. The syntax will never, ever lead you to a false conclusion.
In our judicial analogy, soundness means the court system is perfectly safe. If the system convicts you, if it proves the formula, you are guaranteed to actually be truly guilty, semantically valid. No innocent person ever goes to jail.
Completeness is the exact reverse. Completeness dictates that every single valid formula, every statement that is semantically true in all possible models, is guaranteed to be a theorem. There is no true statement that is mathematically beyond the reach of your syntactic proof system.
So completeness means that if you are truly guilty, semantically valid, the system will absolutely definitely catch you and convict you. No guilty person ever escapes. If a logical system is both sound and complete, it is a flawless, perfectly closed loop. Everything proven is true, and everything true can be proven.
And the text walks us through the exact mechanism of how we prove soundness, using a technique called mathematical induction.
Now, this isn't normal induction, like saying the sun rose yesterday, so it'll rise tomorrow. This is rigorous mathematical induction. It's the domino effect.
To prove an infinite line of dominoes will fall, you don't need to check every domino. You just need to prove two things. First, the base case. You mathematically prove the very first domino falls. Second, the inductive step. You mathematically prove the rule that if any given domino falls, its momentum is guaranteed to knock over the next one in line.
Cider uses a great visual for this. Imagine a massive grid of dots. The base case is proving that the bottom row of dots has a specific property. The inductive step is proving that the rules of the grid, how the dots connect upwards, always preserve that property. If the foundation has it and the upward rules preserve it, then the entire infinite structure above must have it.
So how do we apply this domino effect to prove soundness? We use induction on the length of a proof. Every axiomatic proof is just a sequence of numbered lines. The base case is the starting point of any proof.
The axiom.
We mathematically evaluate the axioms and prove that every single one of them is semantically valid. They always evaluate to one.
The foundation is solid. The first domino falls.
Then the inductive step. We look at our single rule for moving down the lines of a proof, modus ponens. We mathematically prove that if you feed valid true formulas into modus ponens, it will only ever output another valid true formula. It is a perfectly sealed pipe.
So, if line 1 and line 2 are valid axioms, the base case, and your only tool for creating line 3 strictly preserves validity, the inductive step, then line 3 must be valid, and line 4, and line 10,000. Every single line of any infinitely long possible proof in the system is mathematically guaranteed to be a true statement. You have proven soundness. The syntactic universe and the semantic universe are one and the same.
It really is an architectural marvel of human thought.
What a profound journey. Let's trace our steps back down the mountain. We started by defining genuine logic as truth preservation by form, learning to ignore the messy drywall of human language and focus purely on the structural constants.
We built a pristine sandbox, carefully separating our object language from our meta language, learning why confusing the word Philadelphia with the actual city will collapse a mathematical proof.
We looked at the intense philosophical debates over what consequence even means, semantic models versus proof-theoretic steps, and how tinkering with those rules to create a three-valued logic actually changes our view of time and free will in the sea battle.
We journeyed into the heart of set theory, exploring the vicious loop of Russell's paradox, proving that the dense sea of fractions is exactly the same size as the counting numbers, and using Cantor's diagonal argument to prove that the decimals are a fundamentally uncountably larger infinity. The restaurant simply ran out of seats.
We built propositional logic from scratch using recursive definitions. We endured the rigidity of axiomatic proofs, realizing that the agony of the student is a necessary sacrifice to give the meta-logician a beautifully simple system to study.
And finally, we used mathematical induction to prove that in standard propositional logic, the semantic models and the syntactic proofs map onto each other flawlessly. The judicial system is perfect. It is sound and complete.
You now have the fundamental toolkit. You have the logic literacy to resist the symbol mongers, to look at a complex argument and evaluate its architectural skeleton. You know how to read the sheet music, But before we conclude, I want to leave you with one final deeply provocative thought, something from Sider's preface that we haven't fully addressed.
The author explicitly mentions in the preface that this textbook omits Gödel's incompleteness theorems. And if you have been tracking with the architecture we just built, the name of that theorem should be deeply unsettling.
We just spent the climax of this entire hour proving that propositional logic is perfectly sound and complete. Everything true can be proven. It is a pristine, flawless loop.
But propositional logic is ultimately a very simple sandbox. It only uses and, or, and not. What happens when we try to extend our logic? What happens when we try to formalize more complex mathematics, like basic arithmetic with addition and multiplication?
That is exactly what Kurt Gödel explored in the 1930s. And what he proved mathematically is that in stronger, more complex logical systems, completeness catastrophically breaks down. Gödel proved that any consistent formal system complex enough to do basic arithmetic will always, inevitably, contain true statements that can never be mathematically proven within that system.
The perfect loop snaps. The syntactic universe of proof can no longer reach the entire semantic universe of truth. There are true facts out there that the machinery of logic can never, ever touch.
So if propositional logic is our perfectly closed loop sheet music where every single note is accounted for, what does Gödel's discovery say about the ultimate limits of human knowledge when we try to write the symphony of the entire universe? That is something for you to mull over until our next deep dive.